In Chapter 1, we're going to be looking at matter and we're going to be looking at how we measure things. If we look at matter, first of all, there are two possibilities. It's either something pure or it's a mixture. If it's something pure, there's two major classifications, and one is that it's an element. If it's an element, it's made of atoms all of one substance, so it's all magnesium or all selenium, all carbon, whatever. Compounds, though, have atoms of the elements, different elements, joined together in a formula. And we say in a formula because sometimes it's molecules, meaning a little unit of atoms stuck together, or sometimes it's just a ratio and you get a crystal lattice and there's no unit. And we'll go into that later. The compounds have these atoms joined together in a specific ratio, which we write in a formula. The properties of that compound are nothing like the elements. So, for instance, iron and oxygen, both are elements. They combine to form compounds like iron 3 oxide, which is also called rust. And if you look at rust and you look at iron and oxygen, you see they're nothing like each other. So the actual combination changes the chemical properties completely. If we look at mixtures, there are two major classifications. One is a homogeneous mixture, and the other is a heterogeneous mixture. Homogeneous means the composition is the same throughout. So if you look at a Coke, you pour Coke out into a glass, and besides the bubbles, the solution of the Coke is the same throughout. You don't have more sugar in one place than in the other. But if you look at something that's heterogeneous, for instance, a steak, there's bone, which is different from the muscle fibers, which is different from the layer of fat on the outside. And we call that heterogeneous because the composition is not the same throughout. We organize our elements into the periodic table, and this has all these columns and rows. We call the columns families or groups, and we call the rows periods. But the organization of the periodic table gives us some information that helps us to do chemistry. First of all, on the left side of the periodic table over here, we have the metals. On the right side, the right upper corner, we have the nonmetals. And then right down here through this, your book calls it a staircase because it goes, we have the metalloids or the semi-metals. And so just by looking at the position of an element in the periodic table, we know what type of element it is. We have names for some of the groups: the alkali metals, the alkaline earth metals. The two columns here and the 6 columns over here are called the representative elements, and those are the ones that we do the most chemistry with. This one second in from the right is called the halogens, and the last column is called the noble gases or the inert gases. Down here in these 10 columns, we have what are called the transition metals. And the transition metals have their own chemistry that are different from the representative elements, which are left over up there. And we'll use them, but not really understand too much of what they do. We're going to be using them. They're important. Last of all, we have what are called the rare earth elements. Down here in these 14 columns, you have sometimes what is called the intertransition elements or the rare earth elements. These used to be kind of an oddity, but now the elements that are in this block are becoming very important to us because they are important in making the semiconductors that we have in our phones and computers and everything, and they're becoming very valuable because of that. Elements that are common in human biochemistry are the hydrogen, carbon, nitrogen, and oxygen. Those are the most important ones, and that's what makes up a huge amount of the mass of your body. Calcium, magnesium, sodium, and potassium, those are all electrolytes, and the calcium makes up your bones too, along with carbon and oxygen. Then we have phosphate, not carbon and oxygen, phosphate and oxygen. Then we have these transition metals in here that are very important. Selenium, iodine, fluorine. Sulfur is very important in your chemistry. So all these elements we're going to be seeing a lot more of, and some of the others too. The formulas are important to understand because they give you the number of atoms of each element. Now, sometimes when we write a formula of a compound, it is a ratio because there are no molecules, and it's just you have a crystal lattice with billions of fluorines and billions of maybe magnesiums, and they're in a 2-to-1 ratio, but there's no individual unit that comes out of there. But sometimes we have what are called molecules, a unit of atoms attached to each other, and they stay stuck to each other all the time and move around from place to place, but they always stay attached and in a specific geometry. To understand these formulas, first you realize that the subscript indicates the number of atoms. So glucose is C6H12O6. That's 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Okay, and I didn't write that in. A molecule of glucose contains 6 carbons, 12 hydrogens, and 6 oxygens. Rust is 2 irons and 3 oxygens, and it comes as a crystal lattice. Glucose is a molecule. The glucoses move from place to place. Sometimes you'll see parentheses. An example here is calcium hydroxide shown here. The inside of the parentheses is a unit, and it sticks together. It's very hard to break apart. That unit is very hardy. What the parentheses say is it's a unit, and we only use parentheses when we use subscripts. The subscript here is saying there's 2 of that unit in this formula. So in this calcium hydroxide formula, we have 1 calcium atom, 2 oxygen atoms, and 2 hydrogens because there's 2 of what's inside. So you go ahead and try this. Determine how many atoms of each element are in these formulas. If you pause this lecture, you have more time to figure out the answer. So remember, you have that tool. Okay, if I look at this formula, I have 1 magnesium. I have 2 carbons in this unit, and there's 2 of them, so there are 4 carbons. There are 3 hydrogens in the unit, and 2 of them, so there's 6 hydrogens. There are 2 oxygens in a unit, so there are 4 oxygens. So in this formula, there's 1 magnesium, 4 carbons, 6 hydrogens, and 4 oxygens. Go ahead and do the next one. In this formula, we have 4 carbons and 10 hydrogens. We're going to be making measurements in this chapter and throughout the book. And measurements, scientists like to record measurements by their significant figures, and it indicates how much precision there is in the measurement. These significant figures are used by the book. The way that you write your number indicates how many significant figures it has. And then you take those into account when you express the answer of a calculation. So realize that the book is going to be doing the significant figures and giving you answers into significant figures. I'm not going to go into this with you. I'm not going to take the time to do it. But the reason is that if you learn sig figs, then you're going to go into the medical field. And now medical researchers use sig figs, but people who are practicing medicine do not use significant figures, and they have another way of writing their numbers, and I don't want to confuse the whole matter. So we're going to skip over this. The problem is that the answers in the text and the online homework system are going to be expressed in significant figures. So you might obtain an answer like this right here, 2.56723 on your calculator, and you say, okay, that's my answer, and then you compare it to either the online homework system or the answers in the book, and it says 2.57, and many of you will be alarmed thinking you don't understand what you're doing because you got a different number. But to me, these two numbers are of the same magnitude. What is different is how you're expressing them in sig figs, and they're really the same number. So don't let this bother you. Just skip over it. If you can round your number off to theirs or their number off to yours, you probably did it right. If you have any doubt, come see me and I will let you know. Now, we will be using measurements, and all measurements must have units. If I say the length is 10, this is meaningless because it could be 10 feet, 10 inches, 10 miles. The units give the numbers meaning. And those of you who are going into the medical field, units are essential to keep from killing people. Because if the doctor says give him 0.2, and he means 0.2 micrograms, and you think 0.2 milligrams, you might kill the person. So you need to make sure that every number you write down has a unit after it, if it requires one, if it has a unit for meaning. So on your exams, you're going to be writing numbers. Every time you write a number, even if it's within your calculation, you must have a unit on it, or I deduct 1 point for every unit missing. That can add up to a lot of points. And the reason I do this is it is an essential habit to be developed. If you do not develop this habit, you're going to be at a great disadvantage in doing things correctly. So right away in your homework, start developing this habit.